strings with an odd number of ones. Okay? So take a minute. Yeah, okay, so I had in mind, because I cheated and got it from the book, I had in mind a different solution. The question, first of all, is, does this work? Okay, and why not? 0, 1, 0. So you get 0, 1, 0. You end up in Q1 and you reject. Okay, so it looks like this one is not quite right. More formal. Okay, all right. So I think the homework questions have you doing some design, and it's a puzzle. It's just a puzzle, really. This take a little time to do. All right. So now that we have a fairly clear idea of what a finite state machine is, both formally and informally, and we have done a little bit of design, there are things that we can prove about finite state machines, and in particular, there are things called regular operations. Regular operations. So one is called union. So actually, I'm just one more term. Sorry. One more term here. Definition: a language L that is accepted, recognized by some deterministic finite state machine is called a regular language. Okay. All right. And then we're doing these regular operations, which is union over regular languages. Okay, so this is a theorem. Well, actually, maybe I should define union first. So A and B are regular languages. Okay. Well, each language is a set of strings, so these are sets. Okay, A is a set of strings, and B is a set of strings. It happens to be that A is a set of strings that's recognized by some deterministic finite state machine, and B is a set of strings that's recognized by some deterministic finite state machine. Okay, but they're still the sets. So what kind of things can you do with sets? You can take unions, you can make intersections, you can make differences. What's the exclusive or difference? You can do all kinds of things with sets. You learn that in high school. So you can think about the set A union B. Okay? That's the set of strings that are either in A or in B, or maybe they're in both. Okay? So we can ask, is A union B a regular language? And the theorem is yes. So if A and B are regular, then A union B is regular. Okay? That's a theorem. That's something we can prove. Now, is that really clear what it's stating? Again, think about A as a set of strings, and B as a set of strings. It happens to be a set of strings that's recognized by some finite state machine, and B is a set of strings recognized by a finite state machine. But because they're sets, they can be union, and so we can think about A union B, and this theorem says that if A and B are regular languages, then A union B is also a regular language. Okay? How do you prove that? Well, what's the only way we know so far to know whether a language is regular? Yeah, if it's recognized by some deterministic finite state machine. That's the only way we know so far. We're building up some tools, but so far, the only possible way of exhibiting or proving that a particular language is regular is by showing a deterministic finite state machine that actually recognizes that language. Okay, so we want a deterministic finite state machine that recognizes A union B. And on the assumption A is a regular language and B is a regular language, we know what about them? We're accepted by what? Accepted by what? Okay, some. Okay, so A and B? No. So the question here is, what was being suggested here was ultimately getting to the point that what we know about A is that there is, because it's regular, there's some deterministic finite state machine that recognizes it. And what we know about B is that there's some deterministic finite state machine that recognizes B. Okay? Again, by fact, really, the only way we know that a particular language is regular is the fact that this fact, this definition. And so under the assumption that A is regular and B is regular, we know that there's a deterministic finite state machine that recognizes A, and there's another one which doesn't have to be the same one. It can be different. That recognizes B. Okay? So we've got these two deterministic finite state machines that recognize two different languages, and now we somehow want to use them to build, or to talk about how we would build if we actually literally had the finite state machine for A and the finite state machine for B. If we had those in our hands, how would we use those to build a deterministic finite state machine that recognized A union B? Any ideas? Well, union is kind of like an OR, right? You're saying, well, I'll accept a particular string if it's accepted by A or it's accepted by B. I mean, if it's in A or if it's in B. Okay, so you might think you did the following thing. Here's the finite state machine M1 that recognizes A, and here's M2 that recognizes B. So we have these two deterministic finite state machines, and one accepts if only if a particular string W is accepted either by A or by is in A or in B. Okay, so take something as an accept. If you accept here, you go to there, and if you accept here, you go to there. This is okay to do. You can say, well, whatever the accept states were here in this machine, I'll go, except for what? So this doesn't have a character on it. Okay, so, all right, sorry, that was silly. I guess make the final states of M1 or M2. That's fine, in terms of description of the finite state machine. But what is this thing doing? We've never had one like this before. There's no character on here. Okay, so what character would you put there? Well, if your language is A and B were nice, that the ones that this accepts always starts with 0, and this always starts with 1, then that would work. But if they can both start with zeros, then we don't know what to do. So what I'm trying to motivate here is that the obvious thing to try, which is something like this, because the union is like an OR, and this kind of looks like an OR, that isn't going to work. Okay, so this is a good first attempt, but it doesn't quite work. We don't have an OR in deterministic finite state machines, and we don't have edges. They don't have symbols on them, the characters on them. So this isn't going to work. So, anybody have another idea?
Yeah, I have a question. Could you maybe show an example of what a language that isn't regular language looks like?
Well, a language that isn't a regular language.
Because I feel like you could have almost any set of strings that are take a finite state machine that would recognize that.
Okay, we're actually out of time, but this course will not only show you one, it'll prove that particular languages are not regular. Okay, so that in fact is something we're going to do, and fairly quickly. Somebody asked to see a non-regular language. Is that person here who asked that? Okay. Well, in that case, I'm not going to go into it. We will actually, not this lecture, but probably the next lecture, we'll see languages that are not regular and prove that they're not regular. So what I was going to do, if this person was here, was just show him one, and then he could go home, or you can go home and fiddle with it and try to find a finite state machine for it and fail. And then maybe build up your intuition. Actually, let me do that anyway. So try this one. The language is going to be the set of all strings, A to the N, D to the N, where, well, N is it's the same N here, okay? So, N can be anything. N can be N greater than or equal to 0, okay? So, what this means is the following, like A, D is in a language because it's the same number of A's and B's. Okay? By the way, this symbol A, that's the number of the alphabet, raised to the N, that just means repeated N times. Okay, that's in the book, you might not have read that. So A repeated N times followed by B repeated N times. Okay, so that's a language, it's a set of strings. There's another member of that language, double A, double B. Okay, that's repeated twice. ABA is not in the language, right? Okay, because that's certainly not A some number of times, then followed by B the same number of times, because you have this extra A there. Or similarly, AAB, that's not in the language because it's two A's followed by a single B. All right, so this is a language, it's a set of strings, but I'm claiming that this is not a regular language. You can try to build a finite state machine for this, but you should fail. Okay, and in a couple of lectures, we'll actually prove that there's no finite state machine that can recognize this language. Okay, so sit with that if you have time, and then build up your intuition a little bit for when we get there. All right, but what I actually stopped with last time was the following claim. Let me remind you what the union of two regular languages is. So union of regular language A and regular language B, that's the set of strings, X, where X is contained in A, or X is contained in B. Okay, and you notice this or. So when you think of a union of two languages, you can think of that union is essentially talking about an or of two conditions. This is the condition for being, I was just saying it's in A, whatever it takes to be in A, that condition, or the condition of whatever it takes to be in B. I haven't told you what A and B are specifically, but those are two regular languages. Okay? And then the theorem that I stated, or the claim that I stated, is that if A and B are regular, then A union B is regular. Okay. And again, I'm using the fact that A is a set. It's a set of strings, and B is a set of strings, and so as sets, it makes sense to take the union. A union B is a set of strings. Okay. So we're assuming that A is a regular language and B is a regular language, and we want to show that A union B is a regular language. We're also, along the way, I don't know why you don't state this explicitly, but we'll show that A intersect B is regular also. So again, with two different sets, you can apply set operations to them. Okay, so but we'll do proof first for A union B. And what I did last time was to show you a mistaken approach. Okay, we said, well, A is regular. So what does that mean that A is regular? What's the only thing we really know about a language if we go to this regular? What's the thing I can say about it? Yeah, there's a deterministic Christ machine that recognizes it. Okay, so what kind of, it gives you this misdirection. It first defines, it talks about machines accepting a language, and then it says, but don't do that. Don't say that word. It's talking about machines recognizing a language. Okay, so we know there's a deterministic Christ machine that recognizes A, and we know there's a deterministic Christ machine that recognizes B. And that's basically all we know about it right now. That's all we know about what it means to be a regular language. So let's say there's this M1 recognizes A, and M2 recognizes B. Okay, and these are two deterministic finite-state machines. And then, because the only thing we know about what it means to be a regular language is that there's a deterministic finite-state machine that recognizes it. In order to prove that A union B is regular, I have to come up with some deterministic finite-state machine that recognizes A union B. Right? So the general idea is that we're going to somehow use these two finite-state machines to build a finite-state machine to recognize A union B. We want, I'll call it M3, that recognizes A union B. Okay? And last time, what I did, which I said was wrong, is to think about, well, you've got the machine M1 that recognizes A, and you've got the machine M2 that recognizes B. And this is an OR here. The union is really, the string X is in A or it's in B. So we'd like a machine, to build some kind of machine that would go through either of these, and then if either one of these accepts, it comes to a accept state or final state, then we would accept. But we don't have operations like that for deterministic finite-state machines where we can branch two ways, and if either one of those succeeds, well, this is okay because we can just make these for final states anyhow. And we don't know how to branch two ways. We'll actually learn that today. But right now, we don't have that as an operation. This is a deterministic. We need a deterministic finite-state machine, so branching like that isn't a possibility. Okay, so the idea is that M3 should simulate M1 and M2 running in parallel. However you spell parallel. So this idea of simulation is something that comes up over and over again in this kind of material, that with one class of machines, we can simulate another class of machines, or show that a certain language is, in this case it's A union B, is recognized when we have the components M1 and M2. Okay, so let me just show you, first of all, by example, I hope, how this works, and then I'll show you very formally how this works. Okay. Yeah, all right, so we're going to let A be a set of all binary strings with an even number of zeros. Even number of zeros. And B is going to be the set of binary strings with an odd number of ones. Okay. So that's an A, but it's not in B. Okay? So let me see what these two languages are. Now I want to show that, and then A and B are both regular. It's easy. Let's go find a state machine for A. Okay, so M1, we even looked at one, I think, last time that does this. It's an even number of zeros. So There's the start state, which is also going to be the final state. There's a 1. Stop it, 0. 1. I'll give this a name Q1. And we'll go over to Q2 with a 0 back here, with a 0, and here with a 1. So this machine accepts the empty string, which has 0, 0, so that's an even number of zeros. And then you can have any number of 1s you like, but if you get a 0, you can then have as many 1s as you like, but you have to get another 0 in order to get back to the final state. And then you can have more 1s. And, So this generates any binary string, but the only ones that it accepts are the ones that have an even number of zeros. Okay? So this is an easy finite state machine for M1. And then for M2, you want a machine that accepts binary strings that have an odd number of 1s. Okay, and that's similarly easy to do. Here's a state Q1, that's a 0, 1, And the book typically uses the same notation for states in 2 different machines, and that's fine, but it gets a little bit confusing later on when we have to refer to both of them simultaneously, and the book does that by the position and the vector. I like to actually give different state names to different states in different machines, just for greater clarity. So these states will be called Q, and this will be P, and mathematically it doesn't matter at all, but I find it simpler to keep your list value. So this is P2. Okay, so this should be a machine that recognizes the binary strings that have an odd number of 1s. So you can start with any number of zeros. You go over to here, this is the final state, that's 1, 1. You have more zeros. You go over there, that's an even number of 1s, and this is not an accept state, it's not a final state. So in order to get back to where there's a final state, you have to have a number 1, which makes it now an odd number of 1. So this is a machine that accepts the language B. Okay? But now we want a machine that recognizes any string that is either accepted by this one or accepted by that one. And as I was saying earlier, we can't just somehow put them in parallel because we don't have an operation in deterministic finite state machines that does any kind of parallel type branching. So we have to build a third machine that somehow is constructed from these two, but has a different idea. Now, how many people actually, this is the next page where I got to last time in this book. How many people have read that? And some people have, the people who come and talk to me. Okay, right now, for those of you who haven't been, so again, the idea is to somehow simulate both of these. And the idea is that we're going to build a third finite state machine. And its set of states is going to be the Cartesian product of the set of states in M1 and M2. And this is going to be all pairs of states, where the first state comes from M1 and the second state comes from M2. So the states in M3 are going to be Q1, P1, Q1, P2, Q2, P1, and Q2, P2. Right? So this object here is a pair of states from M1 and M2. Right? Also, this object is also a single state in M3. And he has to have a stick like that position, as opposed to somebody off the street. This is just a funny name. Okay? It's a long, kind of awkward name, but it is just the name of a single object, and there was a single state in M3, even though where we got that name from was from a pair of states from M1 and M2. Okay? And we'll simultaneously sometimes refer to this as a pair of states, and then you have to think, okay, pair of states from M1 and M2, or refer to this as a single state, in which case we're also thinking of M3. Okay? So this is a set of states, 4 states from in M3. And then once we hit the starting state of this machine we're trying to build, it's going to be that particular pair of states will be both the starting state. So this is the starting state Q1, this is P1. So it's Q1, P1. Okay. That's the start state of M3. I'll get to the final state in a minute, but now I need to show you what the transition function is. So we're now talking about, again, M3, and so in order to distinguish it from the, now I guess what I better do is the transition function here was going to be called delta 1, transition function here is called delta 2, and this one will just make it delta 3. Okay. So transition function, what's a transition function generally? It's a function on what? What are the arguments? Yeah.
The state and the language.
The state and the what?
It's like a binary language that will be updated.
Okay, and the term more generally is character in the alphabet. So this takes in a state, okay, and a state, and a character, okay, and it goes to a state. Now, think of the alphabet. I didn't tell you what the alphabet for M3 is. It turns out the alphabet for M3 is the same as the alphabet for M1 and M2. They have the same alphabet. And so, what's completely formal and correct, you should say what the alphabet is here for M3 is the same as for A and B. Nothing was same before, just the alphabet for A and B. Okay. So that's what we want. We want a transition function which is over the states of M3 and the characters in the alphabet that go to the states in M3. And we're trying to simulate. Remember, we're trying to simulate what those two different machines would be doing, M1 and M2, whenever they see a particular string. So, again, working by example instead of by total formality, we look at each one of these states in M3 and we ask for each particular character that would be processed in the input string, what do these two separate machines do, M1 or M2? So, for example, what does the state Q1, P1, and it has